Welcome to the Explainer. Our goal here is simple: to take complex topics and make them clear, engaging, and easy to understand.
So let's start with a really big question. How did we as a species learn to count all the way to infinity? It's a huge idea, right? And the answer? Well, it starts with something we use every single day: our numbers. Have you ever really stopped and thought about where our numbers, 1, 2, 3, actually came from?
Well, it turns out the story of our modern numbers, and yeah, that includes the revolutionary concept of zero, it all begins in ancient India. And things like the decimal system or the idea of zero, they feel so obvious to us now, but they weren't inevitable at all. They were the result of this incredible journey of mathematical innovation that honestly shaped the world we live in today.
All right, so first up, let's tackle a really fundamental problem: the problem of scale. Just think about it for a second. How would you write down a huge number, like in the millions or billions, if you didn't have the system we use today? It sounds simple, but for most of human history, it was a massive headache. It was just incredibly clumsy.
Just look at this comparison. It's night and day. Take an older system like Egyptian hieroglyphs. To write the number 999, you needed 27 different symbols. 27. But the Indian system, it only needs 3. So what was the secret sauce? It was making the position of the number matter. A 9 here means 9, but put it a couple of spots over, and it suddenly means 900. That simple idea, that was the absolute game changer.
Now, this brilliant idea didn't just pop into existence overnight. It was a long, slow evolution. You can see the seeds of it way back in the Vedic period, with this concept of scaling everything by powers of 10. Then, a little later, you see these early placeholders for an empty spot, like a simple dot in the Bakshali manuscript. A few centuries on, Aryabhata comes along and makes it official, spelling out the rule: each place is 10 times the preceding one. But there was still one piece missing, and that's where Brahmagupta comes in.
And here it is: 0. This was the final, absolute masterstroke. Because Brahmagupta was the one who said, hey, what if this isn't just a placeholder? What if it's a number? He's the one who laid out the rules for it. What happens when you add it, subtract with it, multiply by it? That single intellectual leap, treating 0 as a number, is what completed the whole system. And honestly, it changed everything about how we do math. Okay, so now we've got this super powerful number system. That's great. But it creates a whole new problem: the problem of memory. Think about it. We're in an age before printing presses, before computers. How in the world do you pass down enormous amounts of data, like, say, detailed astronomical tables, from person to person, generation to generation, without a single mistake slipping in?
The solution they came up with is, frankly, one of the most brilliant things I've ever heard of. It's a system called Bhuta Sankhya, and the core idea is you hide the numbers in plain sight by encoding them into poetry. You take a number and you represent it with a word that everyone already associates with that number. Suddenly, these long, boring strings of digits become memorable verses. Just genius.
Let's dig into a few examples so you can see what I mean. The number 0, you could use words like sky or space because they represent emptiness. For 1, you might use moon or earth, things there's only one of. 2 is easy: anything that comes in pairs like eyes or arms. 4 could be the Vedas, the 4 sacred texts, or the 4 oceans. What you end up with is this incredibly creative and rich vocabulary just for talking about numbers. Okay, so how does this actually work? Let's try to decode a phrase together. It's like a secret code. You start with the words, right? Netra, ka, bhumi, and you convert them to their numbers. So netra, eyes, is 2. Ka, sky, is 0. And you keep going. That gives you the sequence 2, 0, 1, 1, 8. But here's the clever twist. There's a rule. The digits proceed from the right to the left, so you have to reverse the whole thing. And boom, that poetic line unlocks the number 81,102. It's just this beautiful marriage of poetry and math. All right, let's shift gears a bit, because all this cleverness wasn't just for abstract stuff like numbers. It was also deeply connected to the physical world, to geometry. And the big problem they were trying to solve was precision. How do you build these incredibly precise geometric structures like sacred altars when all you have are the simplest tools like ropes and pegs?
The answer lies in these amazing texts called the Śulbasūtras. You can think of them as highly sophisticated instruction manuals for building these complex fire altars for religious ceremonies. And getting the dimensions exactly right was a sacred duty. So these priest geometers figured out how to use simple ropes, the Śulba, to do some incredibly advanced geometry.
And get this, tucked away in these texts is the earliest known statement of what we call the Pythagorean theorem. But look at how they described it. There's no a squared plus b squared equals c squared. It's all physical, all tangible. It's about the area that a rope stretched along the diagonal makes compared to the areas from the side ropes. This is geometry born directly from a practical need. And their methods were just so elegant. Take this one for creating a perfect perpendicular line. It's called the fish figure method. You just make two intersecting arcs from 2 points on a line. The shape they create looks kind of like a fish. And if you draw a line right through the middle, connecting the intersection points, you get a perfect perpendicular bisector. Every single time. It's foolproof, and you don't need any fancy modern tools.
This obsession with getting things just right led them to some frankly astounding results. For example, the Śulbasūtras lay out a way to approximate the square root of 2, which, remember, is an irrational number. It goes on forever. And their approximation was accurate to 5 decimal places. That is incredible. It shows they had this really deep, profound understanding of how numbers and shapes worked together. And that quest for precision? It didn't stop there. It just kept going. Centuries later, it pushed a group of mathematicians down in the Kerala region to tackle one of the biggest, most mind-bending ideas in all of math, infinity.
Okay, this is where things get really, truly mind-blowing. We're talking about the Kerala School of Mathematics, led by this genius named Madhava. And what they were doing was essentially inventing the core concepts of calculus. I mean, look at this, an infinite series for calculating pi. This was worked out in Kerala hundreds of years before it was discovered in Europe, centuries before.
There was just one problem, a big one. This series is beautiful, sure, but it converges, well, at a snail's pace. To get even a few decimal places of pi, you'd have to add up hundreds and hundreds of terms. It's just not practical. So how did they get a precise answer? They came up with another ingenious shortcut. It's called Antyasa Samskara, which basically means end correction. Think of it like this. You have an infinite list of things to add up. Instead of trying to do the impossible and add them all, you just add up, say, the first 20. Then you use this special correction formula to figure out a really, really good estimate for what all the rest of the infinite terms would add up to. It's an absolutely revolutionary idea for getting a super accurate answer without doing an infinite amount of work.
And you can't argue with the results. Using these methods, Madhava calculated pi to an incredible 11 decimal places. 11! And then, in this perfect circle back to the traditions we talked about earlier, he encoded that super precise number into a single line of poetry. It's the ultimate fusion of mathematical precision and artistic elegance. So, after all that, what's the big takeaway? I think it's that these weren't just a bunch of random, lucky discoveries. This was a continuous, evolving, and incredibly powerful tradition of mathematical thinking that truly did have a lasting impact on the entire world.
So let's just quickly recap the 4 huge contributions we've walked through. First, the decimal system with 0 that basically powers all of modern computation. Second, those ingenious poetic systems for encoding numbers, solving the problem of memory. Third, the practical geometry of the Śulbasūtras, which turned a religious need into universal geometric truths. And finally, the Kerala school's breathtaking leap into the ideas of infinity and calculus centuries ahead of their time.
And you know, it wasn't just us looking back and being impressed. Some of the greatest minds in history recognize this debt. Just read what Einstein said. He basically argued that without being taught how to count properly by the Indians, modern science just wouldn't have been possible. That's how fundamental this stuff is. And that leaves us with one last, really fascinating idea to chew on. The Pythagorean theorem, the value of pi, infinite series. These are universal truths of the universe, right? But the path to discovering them doesn't always look the same. Here, we saw them discovered not with the kind of symbolic algebra we use today, but through physical ropes and geometry, and even through poetry. It really makes you think, doesn't it? How many different ways are there to arrive at the same fundamental truth?